Hi everyone. My name is Nikhil Barthwal, and I'm going to talk about Event Driven Microservices Architecture in a functional language. The way I wasn't sure what kind of audience I have, so the way I've basically oriented this talk is it's more of an application of functional programming to distributed systems, right? Now, all my code examples happen to be in F#, but from a concept point of view, whatever I say is equally applicable to Scala or JVM folks. So if you happen to be from the JVM side, I don't want you to feel left out. Okay, so specifically, my objective with this talk is, one, I want to show why functional paradigm is great for implementing event-driven microservices, right? And secondly, how would you implement them using programming language constructs? Okay, so start with the basic, right? We have the monolithic, the old school approach. You have a web service, different clients. You have a database, single service, simple, easy to deploy, just about everything works, but it doesn't scale. Why it doesn't scale? Well, to start with, you have a large code base, right? So large code base means slower development. Your developers have to ramp up. It's also more time to test and deploy. And when you have a large code base, which is very like what they call in literature as big ball of mud, you make one change and you could break several parts elsewhere. So it's hard to change, right? Because there's no very clear-cut boundaries defined, and that's the problem with monolithic. Most of the people would start their web services with monolithic, and at some point of time, they would migrate to the brave new world of microservices. And obviously, there's so much of team interdependency because every team, basically, you're working on the same code base, right? So for team A to release a feature, you have to deploy this whole app, which means everybody's changes get deployed. So there's a lot of coordination. You can't write independently. Team A cannot deploy its services without, taking all the team B, C, D into account. So then we move to the microservices, right? Microservices, small and autonomous. So that's like a single responsibility principle. They're focused on doing one thing really well, and typically, a team would own one or more microservices, right? So that's kind of independent, and it has like a well-defined boundaries. The services themselves are stateless, but they might have a database attached in some cases, depending on your architecture. And because they are small, they are faster to test and deploy. For example, Dead.com, I know Don mentioned this company, has about 1,000 services in production. Uber, for instance, has about 7,000 microservices as of last summer. Things might have changed, probably increased, not decreased. So microservices architecture, right? We talk about this approach where rather than having one service, we deploy our application as a set of smaller services. Each service, it kind of runs its own process, it has its own memory, and it communicates with lightweight mechanisms. Very often it would be something like an HTTP. You could also have like a message broker. Kafka is probably the most popular message broker, and you could read and write using TCP Kafka clients. And there's got a lot of good reference for microservices. Sam Newman, he was in this conference. I just had coffee with him day before yesterday. I'm not sure if he's still there now. So these references can go into the details. So I'll just briefly cover microservices. What are the advantages? Like independent releasability, right? Each teams are independent, so team A can release its services without coordinating with other teams. You also have a better scaling. Why do I say you have a better scaling? Let's say your application consists of 1,000 services, and one part of that service is overloaded, right? In a monolithic, if you have to scale up, because it's one unit, you scale up everything. Whereas in a microservice, you can just scale up the parts and not scale the rest of them. So it gives you better scaling properties. It's more cheaper to operate that way. Technology heterogeneity. In my previous slides, I don't know if you noticed, but if you look at those services, some are implemented in Scala, some in C++, and so on. So you can use large number of technologies. You're not confined to one technology, whereas if you have a monolithic service, you only have to use one particular technology, whatever that technology is. You have more resilience, right? If one particular service fails, your remaining, let's say you have 1,000 services, the remaining 999 services would still work. They don't get affected. And ease of migration, big factor. Let's say your technology stack gets rewritten after a couple of years, right? So let's say you're migrating your application In a monolithic, it's all or nothing. So if you have to migrate, you have to basically rewrite everything. Kind of Facebook sort of landed in that situation, and that's the reason why they had their application in PHP, and PHP doesn't scale. But they had this huge code base. They couldn't have migrated so easily. So instead of migrating, they actually made PHP faster. So that's how Hack and hip-hop virtual machine came into existence. But big factor is migration, right? In microservices, you can take one bit at a time and migrate it to a newer set of technologies. So let's actually look at what a microservice is from a functional programming point of view, right? A service is basically a function, right? You have an input event, and you have an output event. And this is a pure service, which is how majority of the services generally tend to be. Pure means they don't have any side effect except logging. Now I'll explain why I don't include logging as a side effect. But imagine this. Let's say you're running some Amazon or Jet.com e-business site. You place an order, right? Your life is an immutable thing, because if an event happened at T, it happened at T. There is no way you can reverse that, in the sense that you can't go back in time and change, right? You could particularly cancel that event or generate a new event at some particular time, but that's a separate event, right? I place an order today, I've placed an order today. I can cancel that order tomorrow, but that's a separate event. But I can't go back in time and change what I did. So this is how service mathematically would look like. A web service is essentially a function that takes input and generates an output, right? And it doesn't really have a side effect except logging. The reason why I don't consider, and I know Haskell people would kind of disagree with me, but the reason why I don't consider logging as a side effect is, to me, in context of web service, a side effect is something that changes the state of your system. Logging doesn't do that, right? Logging is just pure dump of what's happening, that's all. It doesn't really affect the running of the service in any way. It doesn't change the state. In this case, the service doesn't even have a state. But let's say you have a database attached to it, right? So this is an impure service. It's an impure because you have a database, and there's an IO to database, so you have a concept of state. So you could mathematically model it as, I have an input and I have a state of my DB, right? And then I have an output response, and I alter the state. Basically, if you're using some kind of CRUD, then basically you're essentially running a query to modify that DB state, right? So that query becomes an output in a way. And if it's an event sourcing, then you're generating an event. So that's how microservices would look like from a functional programming point of view. So before I go into how you would implement service architecture using functional programming, I sort of wanted to reflect back on why object-oriented programming is not the best way to implement them in the first place. So the thing is that when you think about object-oriented programming, object-oriented programming basically has its roots in imperative programming, right? You had languages like C and Fortran, the early languages. And what C and Fortran basically were they were designed to manipulate the Van Neumann architecture, right? You have a simple memory, your state, and you basically have a set of state transitions, your assignments, so on. So you basically have states, and you're transitioning to states. Obviously, languages like C and Fortran doesn't scale, so in 1980s, I know there was a lot of talk on the history, there was small talk and so on, so C++ came into an existence as an extension of C, and object-oriented programming wasn't exactly born around the same time because it started with Simula and Smalltalk, but that was where it entered the mainstream, right? And what object-oriented programming brought to the world of imperative programming was two new features: encapsulation and polymorphism. But the point to be noted is it was still a kind of state transitioning system, because when you look at an object has attributes to it, right? And it modifies the attribute. Essentially, that's the state of that object. Those private attributes modify this, is the state of that object, and you access them either directly or through the interface that object exposes. But it turns out that, as we just discussed, microservices don't have states. So what's weird to me is that you are using a language that was designed to manipulate state, and using that language and implementing it in an architecture which basically doesn't have state. So that's the disconnect. This is what makes object-oriented programming. I know vast number of people still use it, but this is what's there in mismatch. It's not the right match, right? like I said, OOP just extends encapsulation and polymorphism, but it's still manipulation of states. And imperative was designed for Van Neumann architecture, but today, you don't interact with the Van Neumann architecture directly, right? You have, in case of .NET, you have the CLR. In case of Java, you have the JVM. So you have this virtual machine in between that kind of abstracts out your operation, so you don't really have to worry about interacting with the Van Neumann architectures. You don't have to really worry about the state or the memory directly. And one of the things that OP people like to say is we have a very good ecosystem. I show Java and C# have been around for long. You have tons of library. But when you look at the new languages like F# and Scala, they can interoperate with C# and Java pretty seamlessly. And I don't know how many of you were in Don's talk, but he talks about F#, right? And he did mention this several times. During the design of F#, interoperability was a very important design constraint that we take into picture. So pretty much in fact, all the libraries that you have in Java and C# are now available in F# and Scala, right? So this statement that, there's this myth that functional languages, they are not very, you don't really have a very good ecosystem. That was true in the 90s and probably early 2000s. It's not true today. This was like it's probably, if you use something like OCaml or Haskell, because they have their own runtimes, this statement is partially true, although even in their case, you have a foreign function binding, so you could possibly interact with the libraries in C, but sure, there's extra work involved in it, but with F# and C#, you don't even have to do that. It works seamlessly with C# and Java. So let's look at how you model a service using functional programming construct, right? When you think about a service to a functional programmer is essentially a function, right? A web service takes an input, takes an event, and outputs. It's just to say that function takes an input and shows an output, which is what we saw in the functional view of the service, right? Y is equal to fx. And then in event-driven, particularly in context of event-driven, you have these events, right? So you can model these events using algebraic data types. F# calls it discriminated union, Scala calls it case classes, but Haskell, I think, still calls it algebraic data type or whatever. But it's the same thing, right? We're all talking about the same thing, and we'll see some examples of algebraic data types and how you model later on in this talk. So events are immutable. Well, FP kind of guarantees immutability because life is immutable. You can't go back in time and fix something. And services generally tend to be stateless. I mean, in some cases, you have some database attached, and functional programming encourages writing pure code. I mean, if you see the motto of F#, it says it's functional first, right? And what that functional first means, the language is primarily designed to be used in a functional manner, but that said, it's a multi-paradigm language, right? You could potentially use object-oriented, and you can use all the mutating variables. You have to explicitly mark them in F#, but it's possible to do it. But by and large, the recommended programming style is to use the pure code as and when, and use the impure only when it's really necessary. So what all this means is that the service architecture, the event-driven microservice, or generally web services, functional programming captures that architecture very naturally, because all your physical concepts map to functional concepts pretty much one-on-one. So I'm going to go into some examples of F#. So let's say I'm making a search, right? I'm making a search on a catalog page of whatever website, Amazon, Jet, etc. I can search that item from its name, or maybe the catalog number, SKU as they call it, right? And I have an output. The item is in inventory, item is not in an inventory. And basically, my web service then just becomes a function. Now, when you look at object-oriented programming, the way people, or you should do, or the recommended style usually is that in your architecture, you would take your problem and you would design classes for it, right? And initially, you just have all the attributes, the private, public attributes, and so on. And once you have all these classes, you start implementing those methods in your code. The way you do functional programming is you first write all the types for it. And then you write these functions that takes those inputs and outputs. And once you have that, that's your architecture. And then you can start implementing the code. So that's how you would model the service. You would take all your events, you would model them as discriminated unions or ADTs, and then you model what are the services I need, these are the functions, and then later on you start implementing them. You also have asynchronous workflows. For example, I can have something like, I've placed an order, so the order stock service receives an order, it gives you an acknowledgement, right? I've received your order, that's synchronous, so you want it right away, and then it sends an async code back to the shipment service, I've received an order, ship it when you have time or wherever. So that's the code for it. In this one, you have the first response happening synchronously, the second communication is asynchronous. So, it can send an async. You don't really need to do an acknowledgement from the shipment. You don't have to wait for it. That gives you scalability to your code. Okay, so the whole essence of microservice architecture is that you have loose coupling, right? You have loose coupling, you have all these different APIs, and then you have different databases. So you have one database per service, right? Not every service would have a database. You could have services that are pure, but generally you would not have more than one database per service. There are some people who basically, what they do is they have like one database for multiple services, and that's the worst thing to do. Because when you have a distributed database, you're bringing some problem of distributed data. And when you have such a pattern, you inherit all the bad things of microservices architecture. You inherit all the bad things about monolithic, and that's the worst thing to do. So never do that, okay? If you're sticking with monolithic, and that's okay, I mean, there's nothing wrong with monolithic, except it doesn't scale. So if you don't need to scale, it's fine. There are a lot of advantages to monolithic. So it's not an anti-pattern as such. But you have to understand its limitation. Now, if you're doing microservices, you want a database per service. So that's how you achieve loose coupling. So loosely coupled services means you have reduced team interdependencies, right? You have reduced team interdependencies means faster innovation. Yay, that's the good stuff. Obviously, there is some bad stuff associated with that, and I'll talk about that. But let's talk about the good stuff first. So now we know that our team, you need to have data and you need to partition it, but the question is how. Now, before I answer that question, I'm going to digress a little bit, and I'm going to go into domain-driven design, and then I'll come back and see how we can apply domain-driven design to the problem of how we should basically distribute data. So domain-driven design itself is a big topic. I would cover it really briefly. It's basically an approach. That's the textbook definition, right? So you have your model of your system, and basically your software development would connect that implementation to the model, right? So you model whatever you're happening in form of your classes. In object-oriented programming, you could do ADTs and functions and functional programming. There is some excellent textbook. Anybody familiar with DDD would know who Eric Evans is. If you're interested in DDD, functional programming, that's the book you want to refer to. Scott was here in the conference. I just chatted with him in the morning. I think he has left by now. And then you have implementing DDD if you're more interested in the practical aspects of it. And domain-driven design has certain elements, right? It has a ubiquitous language of how you basically communicate. The stakeholders would communicate with each other. You have a bounded context. Bounded context says that usually for a large application, you can't have one model, right? So you have a set of interconnected models, and each one of them is like a bounded context, right? Sales department may have their own different model than, let's say, HR or some development department or something. And you have the concept of entities and value objects. I don't want to go into details too much because I think it will digress away from the main subject. But I'll just stick at the high level and say that it allows you to have basically your model, complex model into, it creates a strong connect between your implementation and your domain. So it allows the domain experts to collaborate with technical folks. And there's some good reasons why you should actually use functional programming for DDD. I'm going to cover that. But I'll just cover one particular topic in more details because that's the one I'm more interested in, and that's aggregates. What aggregates is it's a collection of domain objects that can be treated together. So for instance, if you're going on an e-commerce website, your order is an aggregate, right? Your order could have items, it could have quantities, it would have like where it should be shipped, address, all those things, but it can be treated as one unit. So that's an aggregate. And this has one root, which is your order ID, and everything inside this can be referenced from this. So that way, what you could see is your domain model essentially becomes a collection of aggregates. That's how you can see, view a domain model. Okay, so now that we understand DDD, we can use DDD as a way to partition the data. Okay, so let's say you have an order service. Order service, you have a customer, you have a product, and what DDD really gives you is DDD gives you, aggregates give you the boundaries where you can partition the data, right? So that's what DDD brings to the table. Now, mind you, this is not, there is no unique way of partitioning. For example, I have the order service and customer service and product service right now as 3 different. I could potentially merge the order service and customer service as one and keep the product service separate, right? So there is no unique way of how I basically dissect my domain into services, but essentially what I have is I have these boundaries. That's what DDD really gives me. So now, let's talk about domain-driven design architecture layers. So you have the user. This is a more simplified picture of how domain-driven designs actually kind of operate. If you go to the literature, there are more complicated architectures like onion architecture and so on. But I've kind of simplified it. So you have the user interface, right? This typically runs on your client. Then you have the application layer. Application layer kind of handles all the transactions, or basically the service part of it. And then you have the domain layer. So bulk of your code actually is going to be on the domain layer. And then finally, you have the persistence layer or infrastructure layer, which is where your databases are. And mind you, these are logical separations, right? So it's not like you would have one service on domain, one service on application, and so on. The services, the way they are done is one service, user interface is unlikely to be in a backend service. But you could have all of these different last 3 layers, particularly in one service. It's very much possible. But the bulk of your code actually goes in the domain layer, right? And value objects, if you read the original literature, actually are immutable value objects. That's what they recommend how. And you could very well use F-sharp's discriminated unions or Scala's case classes for that matter to model the domain layer. And you could have attached member functions to it that modify. So there is one pattern in DDD, it's called anemic domain models. And what it says is that your domain models should not just be getters and setters. And that's an anti-pattern. So you want to avoid domain models here that just don't do anything except retrieve data. So you shouldn't have really anemic domain models, but you should have some operations attached to it. Now, since on the context of functional programming, I actually want to add a little bit here. Now, when you talk about domain-driven design, typically in object-oriented literature, what you have is like design and code, right? You have a design document of your software, then you have an implementation. And design document is what your stakeholders would read. The problem with this approach is that there is no way for you to synchronize the design with an implementation, right? Very often the guy who implements, they make changes to the implementation, forgets to update the design, or the design got changed, but it didn't got implemented effectively. As a result of it, the design goes in one direction, the implementation goes in one direction, they're out of sync very soon. And in literature, we call this as model code gap, right? The model doesn't correspond to the code. In functional programming, there's a very simple way that we can actually avoid this problem. And the way you avoid this problem is because your discriminated unions, or ADTs, essentially you can model your domain as set of ADTs, and ADTs are very easy to understand. So domain stakeholders could read that design, right, and they understand what that is all about. So what you have here is you have a design that is an executable design, right? And this executable design goes with your implementation and it compiles together. So which means if I modify something on the design, but I don't change anything on the implementation side, my code would break at compile. It just won't compile. And the same thing, if I modify the implementation, but do not update the design, same thing happens. So in some ways, model code gap is eliminated once you have a design specification that is an executable one. Obviously, this is not a perfect solution in the sense that you could have certain constraints, like I can have an integer which I know should be between 0 to 100. There is no way for me to put this constraint in my definition of algebraic data type, right? I could possibly point it as a comment, but then it's not captured in my executable design specification. So it's possible for me to violate such constraints that are not captured very well in executable design. So model code gap is not 100% solved, but solved to a large extent. Now, shifting back, we talked about distributed data and we talked about all the advantages of distributed data. The teams are independent. Obviously, it has its own problems. So now we're going to go into the problems. What are the problems with distributed data? The first problem is because your data is not on one database, but it's spread out, how do you keep it consistent, right? I, as a customer, let's say, placed an order. The product database has to be updated because certain items are now going to be, the count of those items are going to be reduced because, hey, I've purchased them, so inventory goes down by a certain number. Also, in the customer database, this information has to be updated. In a monolithic world, you only have one database, right? One big database. It could have logical partitioning, sure, but still, you don't really have a problem of consistency because you have one unit, whereas in microservices, you now have two separate databases. So the problem of consistency comes in, like you want all the databases to be, all the data to be synchronized with each other. The second problem is, how do I query scattered data, right? If I have all my data in one database, it's easy to run a query. But I know I don't have that problem now. I have a different problem where I have the data scattered across several databases. How do I query them? Problems. The question is, how do I solve this? Typically, you could have used ACID transactions, but ACID transactions cannot be used in microservice architecture. Reason? Let's say you have a query, right? You want to run this query. The problem is this customer database is private to the customer service, and this database is private to the product service, right? So you really can't run a query across database. So there's no option of using ACID transaction. It's actually, people talk about all of these microservices and everything as something new. They're actually not new, because when you really look at microservices, what microservice is an application of object-oriented programming to the world of web services. Why? Think of what object-oriented programming is. And object-oriented programming says that rather than having a global state, right, what I have these objects that have their own private states. So that's private, and they expose an interface. So you can't just manipulate or read that state internally. You have to go through the interface. What does microservices say? Microservices says that rather than having one database and one service, what I'm actually going to do is I'm going to split that services into small parts. And each of the service has a database. So think of that database as the state of that service, right? And you can't really read that state. You have to go through the interface. And in this case, the interface is basically the API interface of the service. So that way, your objects basically of object-oriented programming gets replaced by services, and the state of that object, right, the private attributes gets replaced by the database, and the public methods gets replaced by REST API. So really speaking, microservices is nothing but a concept of object-oriented programming applied to web services. And you see the same thing here, right? You have products and you have customers, two different services, private to each other. You can't access them directly, so you can't run an ACID transaction. Well, Fine. I can't use the two-phase commits. Why? Well, it guarantees consistency, but in distributed systems, coordinator is a single point of failure. You can't afford to have that because your system is distributed. Too many things are happening that you can't keep track of. You don't want to have a single point of failure where everything collapses. You want that resiliency built into it. It's very chatty. You have 4n messages, O(n) square retries, so it's not at all efficient, and it decreases throughput. The very reason why you have used microservices is to increase your throughput, make it like high scale, and if locks decrease your throughput, you have kind of defeated the purpose of using distributed systems in the first place. So this is the reason why two-phase commits don't actually work. So the question is, how do we solve the problem of consistency? The answer is, you cannot. So CAP theorem, I mentioned CAP, I don't think I mentioned it, it was written in one of the slides. CAP theorem says that you can't really have consistency, availability, and partition tolerance. You have to choose 2 out of 3, but you can't have all 3. Now, we don't sacrifice availability in distributed systems because availability means money. Imagine if Amazon goes down for 1 minute, how many millions of dollars they'll lose, right? Availability is a no-no. Partition tolerance, you can't really sacrifice that also, right? It's a big system running in many data centers. You can't really have partition tolerance. But what you could potentially sacrifice is consistency. So, rather than using consistency, we go into what is called as an eventual consistency. So what is an eventual consistency? Eventual consistency says that if you do a transaction, my data sources will not be consistent immediately, but over a period of time, they would become consistent. And that's what eventual consistency is. They will eventually become consistent. And this eventually could mean couple of seconds or couple of minutes, right? It's not like it'll happen after 10 days, good Lord, no. Why it's not a big problem? Imagine I'm sitting in Norway and I place an order, and in the Norwegian data center, it's updated, but I'm from US, my information is not updated in data center in the US. That's okay. Why would I care about it? If, as long as that information gets updated eventually, and eventually means, let's say, in 30 minutes. There's no way I can go back to US in 30 minutes, right, and check that. So even if it happens after 30 minutes, I don't care. And if somebody does access within 30 minutes, it means my account is hacked, in which case I'll have bigger things to worry about than eventual consistency anyway. So this is where we enter into the world of event-driven microservices. Now, this is one of those big buzzwords that you keep hearing, event-driven microservices, and often it's very synonymous to microservices. But microservice and event-driven microservice are actually 2 different things, right? Microservice architecture says that I have this application, I have divided it into smaller units, right? Microservice. Event-driven microservices architecture is a subset of that architecture that basically allows you to build systems which are eventually consistent, available, and network tolerant, right? So it's a subset. That is not to say that that's the only pattern available. There are other patterns that would make other trade-offs, right? This is usually the most common one, and if you go to any distributed systems talk, people are crazy about event-driven microservices architecture, and this is the world, and so on. But really speaking, I don't want to talk about other architectures because I have limited amount of time. So I'll talk more about the event-driven microservices architecture. But you're going to understand that this is actually a subset of the microservices architecture. They're not exactly the same as microservice, right? It's a sub-pattern. So let's go into event-driven microservices. What are event-driven microservices? Something happens in the system, a change happens, an event is generated. Good. All listeners get notified, and some take action. And then it's a very highly distributed, loosely coupled architecture. What do I mean by highly distributed? Highly distributed in the sense that there could be many listeners for one producer of a message, right? There could be many consumers consuming that message. And it's loosely coupled because the consumers and producers of the message, they're not exactly in touch with each other. If a good example is, let's say that somebody makes an announcement, right? The person makes an announcement, people in this room hear it, the person who made that announcement does not know who heard it, right? So he just makes an announcement, and some of you may take action. For example, you're in the airport, an announcement is made, flight XYZ is leaving Oslo. People who are boarding that flight would probably rush to the gate. Those who are not boarding will simply not care. The listener who actually makes that announcement does not know whether the consumer or the listener, the person who made that announcement, the producer, does not know whether the consumer actually received that message and did it actually, they took any action on it or not. And this is the reason why it's mostly an asynchronous flow of information, right? The information flows from producer to consumer. There is no synchronous, there is no acknowledgement happening. Just like loud announcement, event-driven microservices. Great. So now at this point, I would introduce the concept of Sagas, which is basically one way of keeping the data consistent. So what Sagas is, it's basically a long-running transactions, and that uses compensating actions to handle failures. I'll expand on this. But Sagas were originally designed in 1987 to handle the problem of consistency across database, right? So they're not really anything new, but they have been lately started applying a lot on distributed systems. Obviously, they had to be modified because back in 1987, we didn't really have a distributed system. So everything was single node, where now we have multi-node, so you have to handle partial failure, like some of the nodes may be working, some of the nodes may not be working. But the way Saga would look like is you have a set of transactions and you have a set of compensating actions or rollback transactions, right? So let's say a transaction happens from T1 to T2, right? So I'm basically, an example is you give me a check and I am going to deposit that check to the bank. So what happens when I give that check to the bank, from the bank, some money first gets deducted from your account, right? That's the first transaction that happens, and then it goes into my account. Sure, and then ultimately everything gets updated, let's say on the records that money has been translated, but we know that there could be failure. So let's say this transaction failed, T2. For example, the money got deducted from your account. Before it could be gone to my account got closed. I closed my account. So where does the money go? The money goes back to your account. So now it doesn't actually get updated. Your records don't get updated that your money has been deducted from your account. Instead, it goes back to the rollback transaction, right? So this is the concept of Sagas, that one big transaction is broken down into series of small transactions, and each transactions have compensating actions. And you can go about it, and each one would have like failures. So this is how you basically deal with the issue of partial failures. So there are different communication patterns that you use. The first one, the most common, is request response. Synchronous, typically you would know it as an HTTP event, right? And there are obvious benefits to it. It's easy to implement, and there's a better error control. Why is there a better error control? Because if you make a call and the call failed, you know it immediately, right? If you're trying to go to google.com and google.com server is down, which doesn't happen very much, but let's say it is, you know it right away, you got a 404, right? So imagine if you're running a customer website and some of your order is basically some of the items you're ordering is not in the inventory. You want to know it right away because you may not want to order something else, right? You can't. The problem with asynchronous is there's no traceability. So I can place an order and then I don't really know what happened with that. Whereas in synchronous, you get a response right away. So it gives you a very good error control, but it has its own drawbacks. There is an increased coupling because let's say if I want to make a change to the buy item, right? Or let's say fulfillment item, there's a very tight coupling. I would have to change a lot of parts. I would have to change the buy items. I might have to change other services. So it increases the coupling, and that kind of increases the team interdependency. So it again goes back and defeats the purpose of using microservices because your whole reason is faster innovation. It's also difficult to scale. Imagine if I add a new service to it, and that service interacts to order service and fulfillment service, right? I would have to make changes to the order service and the fulfillment service also to talk to the new service. So if I add just one component, I would actually have to make changes to the other components that interact with it. So there's a scalability issues and there's a coupling issues, but obviously I get a good error control. Then you have the event-driven. Event-driven kind of avoids that problem. How? Event-driven has a message broker. So this message broker, I can send and receive messages for it. So imagine if fraud detection service goes down. And does it affect the rest of them? No, they can still continue to operate. The messages basically would get queued, and when the fraud detection service comes up, it starts consuming that message, right? Also, if I want to add a new workflow to it, I can add a separate service here that can read and write from message broker. I don't actually have to change anything else. So this gives me the benefit that it's easier to support new scenarios, and there's a better resiliency also, right? But message broker is like your lifeline for your system, right? It's a highly available system. If something happens to your message broker, good luck with that. So these communication patterns, they are not either or. Usually people would use them simultaneously. So imagine you have services and you distribute your services in tiers, right? Tier 1 is something that customers are directly impacted, then you have tier 2, the customers are indirectly impacted, and then you have tier 3, with little to no impact on customers. For example, your order placement service is a tier 1 service. If that service goes down, you can't place an order, right? The system goes down completely, there's nothing you can do. Your shipment service is a tier 2 service. If that goes down, your order might be delayed by a few hours or maybe a day. So it does affect you, but not directly. And then any kind of monitoring the service is a tier 3. If it goes down, it's a problem for the person who's running the system, but as a customer, you don't care if monitoring goes down, right? So that's a tier 3. And typical usage is that the tier 1s generally would have request response, because remember, they interact with customers, so you need a good error control there. Whereas tier 2 and tier 3 are generally event-driven. So now, one of the problems with object microservices is contract management, right? We have talked about all the services they communicate, and the very reason why we are using microservices is everything is independent, but what if I want to change the contract? I want to change that API. All the services that talk to them now have to use the new version of API. You see the same problem with object-oriented programming, right? If you don't really change the public interface of a class, right, you can use the rest of them, doesn't really matter. The rest of the people don't care. But the moment you change the public interface of the class, all other classes that depend on that class will have to be changed. So this is where you break down the independency of all the objects or all the services. So F# has something called type providers, and Don explained it quite well in his talk, and I don't want to go into too much of details of it for time reasons. So you can define your contracts as snippets of XML and JSON, and then you can share them in a shared location. And what type providers basically would do is they can create data types or algebraic data types from your sample XML and JSON. This feature is more specific to F#. If you're using something like Scala, you have other options like Google Protobuf and Apache Thrift. They would have bindings. I'm not sure they have a bindings to Scala or F#, but they'll have bindings to Java and C#. So you can use your F# code. If some people like to have a human-readable messages in their event store. So that's the reason why they would use something like type providers, because they don't want to use binary formats because they want to read what's there in the event source. But if you don't really care about it, the other ones, Protobuf and Thrift, are generally more efficient. We talk about event sourcing. So event sourcing is another buzzword in distributed systems, right? It's basically what it is as your state of a system is modeled as a sequence of events, right? And you store that events, and anything that changes is like a state change. You basically have a corresponding events. And then you could, roll back in particular time in history and you know what the state of the system is. Event sourcing might be something new, but the reality is event sourcing has been used for centuries. And whether you call it event sourcing or not, the concept, you use it every day without realizing. So what event sourcing basically lets you do, and I'll give you an example of it, it enables you to create more workflows because you have all of these events separately stored. So you can combine and recombine to provide new workflows. So let's actually look at some examples of event sourcing. The first example is banking, bank ledger, right? When I go to bank and I open up my account, it creates an account, and let's say the state of the system is how much money do I have in my account, right? Initially, I have 0 to start with. Then every transactions I do, I either add or subtract something. So that's a separate event. And if you look at your bank passbook, it basically on this day, this time you deposited this money, you withdraw. It's a series of events, right? So that's an event sourcing, bank ledger. Version control system is another event sourcing. You create a new initial repository, you have 0. The state of your system is basically the source code, right? Every time you make a commit, you have an event that stores that delta, that state change, and those deltas are combined, and it gives you the current state of your source code. And you can go back in time, you can do a git log, and you can say, okay, fine, I want to go back and see what my source code was on that day at that particular commit, so you can just do a git log, and then you can do a git check. Again, event sourcing, right? So event sourcing has been there for a long time. We just have started using it in the last 2-3 years. They've been applied a lot to distributed systems. Now, here's another good example of creating future workflows, right? So you're using credit card and you're doing all these transactions. And one fine day, you're looking at your ledger and you realize that there was a transaction that happened 5 days ago. That was fraud. Somebody probably stole your credit card and so on. So you go to the bank and you tell them, the bank says, fine, we'll nullify. So what the bank does is that bank goes back in time, removes that one transactions, and then apply all of the transactions that happened, right, and recreates the state. So for example, let's say that fraud transaction was transaction 1000, right, and today you are at transaction 1500. Bank would take all the transactions that it has till 1 to 999, ignore the transaction 1000, and then takes the transaction 1001 to 1500 to 1500 and builds your new state, right, builds your new account. What you basically did was you removed one particular event and recombined all the events. This is what event sourcing gives you. It enables you to create a new workflow. If you did not store your transactions as individual transactions, just as a state, you couldn't have done that. So how do you implement event sourcing in F#, right, or any functional language for that matter? So you have events, right? You have your current state. It turns out that event sourcing is actually very simple in F# because it's nothing but a fold function. What is a fold function? A fold function says that, I have a state and I have a list. And basically I'm taking elements from that list and I'm building that state. If your list represents a set of events, your fold function, which I'm calling here a state aggregator function, can take this and build up the event. So event sourcing in F# gets translated simply as a fold function. Now, one thing that you would think about is that if I have to build the state of the system from scratch every time, it's too time consuming. Imagine if you go to the bank and every time you have to know the state of your account, basically the amount of money you have to add all the transactions that you did in the last 10 years. It's too time consuming. So what people would do as a performance optimization is they would do something like a snapshot state. So I would store the state of my system, let's say, every day in the morning. So if I want to know what's the state of my system today, I can just take the last snapshot state, which was created, let's say, at 12 a.m. today, and then recombine all the events. So I don't really have to go back 10 years. So you can use snapshot as a performance optimization, where you can replace this initial state as a snapshot state. So what are the benefits of event sourcing? I kind of touched upon some of them, but very accurate logging, right? You can go back in time and you can know the state of your system. You can do like temporal queries, time queries. I want to know at this particular time what's happening. you could have, and I'll expand on this, you can have the same applications that can combine and recombine that events and create different views. One good example of this is Facebook. So a lot of concepts that you see in distributed systems, you actually use them in real life, you just don't realize that you're using them, right? And they are often a fancy name to everything, commonsensical things that you use. I'll expand on this one particularly. And then obviously there are some drawbacks, and it adds complexity. We talked about strict consistency, right? You don't really have strict consistency because events are being coming, they are being combined, and longer boot up times, right? Obviously, we talked about snapshot, but if you don't have snapshot, if you want to build the state of the system, you have to recombine all the events happening from the beginning. Even if it's snapshot, I mean, you reduce your boot up time, but it's still not immediate. So one of the patterns that we use, we call it command query responsibility segregation. It's a little bit of scary looking name, but it's honestly very simple. I had mentioned that one of the problems is, how do I query the state of the system when the data is scattered, right? If I'm storing all my state as a sequence of events, I don't really have one particular, I would say, database or some source of truth that I can query. So how do I query? Well, the solution, what CQRS says is, disconnect the read and write, right? Read and writes are separate. Your basically writes would write the event to a database, and then your read service would basically combine those events and create a model that you can query. So that's what CQRS basically gives you. This pattern is a must for event sourcing. Multiple views from a single event sourcing, right? Imagine Facebook, right? You post events in your timeline. You have a photo app, you have a personal event, right? Events happen on your post line. Let's say you post a new photo. Your photo app basically sees that. It adds that photo to your photo album. Your personal section, info section sees that. It ignores it. Then let's say you got married. Your photo app sees that event. It ignores it. Your personal life section says, info section sees it. You got married. It updates your status from single to married. The same event is being interpreted by different services and processed differently. So that's what another thing event sourcing from a single can do is, from a single event stream, it can actually interpret that events and do multiple things with it. So let's say CQRS, it's needed for event sourcing. We know that it improves separation of concern and scalable multiple views, but it adds complexity. There's a lot of code duplication. There's a replication lag. One of the problems is we don't really have strict consistency. Finally, how do we test it? And one of the good advantages of using functional programming is testing is very easy. Why? We don't have state. So I know that my output only depends on input. I can exhaustively test my input and output. Most of my services are stateless, so that's not a problem. There are some states. So for example, let's say that you're checking the billing service, right? Or order management service. I would have the billing service separately, where I'm actually billing the credit cards, and the order service separately, and I can exhaustively test the order service. And billing service, I can just test it mildly, because all I have to test is, if I place an order, does my credit card gets billed, right? So I don't really need to test it exhaustively. There's unpredictability due to the presence of external state. Event Driven Microservices tends to have a little complication in testing. You need a test driver that injects a test event to the message, and unit response. But the fact is that they are implemented in functional languages, means mostly they are predominantly pure. So output is dependent on input, and you can do an exhaustive testing. One of the big concerns of services is actually security. Static analysis tends to be a very effective way of testing it. And again, an advantage of functional programming, the code is pure, which means that static analysis is very effective, right? F#, you can define a set of patterns, and F# can parse into an F# compiler services is a library, I know Don mentioned it, which is used in a lot of tooling, and you can parse F# into AST. Your app, AST can detect all the patterns, right? So it's very easy to do static analysis on functional code. What are the benefits of functional programming? Scalability. Well, you don't have states, you don't have locks, you don't have mutations. Anybody who has done multi-threaded programming in Java, very few people would love it. Most of them I know hate it. You don't have to do all of those now. You get scalability out of the box. Productivity. Your code is much shorter, so you're a lot more productive. Code correctness. Your type system makes unrepresentable states impossible. So a lot of runtime problems that you have on your system, they become static compile time issues. Your compiler would basically check them. There's a joke in F# community, if it compiles, it probably runs. Basically, you've traded all your runtime issues into compile time issues. Everybody hates those null checks. You can use options, you're done with it. In the interest of time, I'm going to skip a little bit of these slides, but essentially what they talk about is you have infinite scalability, massive parallelism because you don't have mutex, locks, and races. You obviously have less code, more concise than C#, which has its own benefits, easy maintenance, easy ramping up. Code correctness, I already covered it. Strict typing makes writing correct code easy. Exhaustive pattern matching. If you miss a case, your compiler would tell you you missed a case. Type system makes illegal states unrepresentable. Finally, I'll end with some actual case studies. Jet.com, most famous, everybody in the F# community knows about them. They were launched in 2015, and finally they were acquired by Walmart 2016 for $3 billion. So at that time, it was the largest acquisition, and they had a record that they were the fastest unicorn ever to reach 1 billion valuation in record time. Some statistics, 8 million, because a massive, massive distributed system. Bulk of their microservices was implemented in F#, a real F# success story. Another functional programming story, which probably people are more aware of, is Twitter. Twitter started as a Ruby and Rails application initially, and then they migrated to Scala. Currently, they are a mix of Scala and Java. So they're not 100% pure Scala. I don't actually know the proportion of how much Java they have and how much Scala they have, but I have some pointers. You can read their articles. But Scala is definitely one of the most dominant languages for backend. So that's another big success story for functional programming. And finally, I come down to the summary. Functional programming is very good for modeling services. We know why. Microservices enables faster innovation. Great modeling events using algebraic data types, Scala case classes, F# discriminated unions. Keep the service pure for scalability. You don't want blocks and mutexes. They are dreaded. Everybody hates them. And functional programming gives you the benefit of scalability, productivity, and code correctness. Thank you. I have 3 minutes remaining, so I'm up for questions. Yes, sir.
More or less a remark. With command query responsibility segregation pattern, one thing you can do is store all the events. So if you create a new model, for instance, like a fraud model, you can even look back in time if there was any fraud in the past.
You can do that, but there are technical problems with it. First of all, it depends on your event store, right? Certain event store, you can read the events in a certain order. So there's a C# implementation of event stores by Greg Young. So what he does is it gives you an indexing factor. So you can index all the events in a certain way. So you don't really have to look at it in a one serial order. So there your pattern would actually work because you can look at it. But generally, the more theoretical definition of event source is that events happen in a certain order. And if I can't just, like if I have to go back in time and read those events, I can't just hop directly. I have to go in that sequential manner, right? Internally. So if I was to look at your problem, one of the ways is, and I talked about one application can process multiple views, right? You can have the application sitting that can process that event stream, and whenever there is a fraud happening, right, it can ignore all the events but the fraud events and build a separate fraud view of it. That kind of solves your problem. Event store gives you out of the box, but you can implement it on your own also. Not a problem. Answers your question? Yeah, any other question?